Welcome to this video on statistical mechanics. My name is Jos Thijssen and this video is part of a series I have made for my students in statistical physics, a class that I teach at the Technical University of Delft in the Netherlands. This video addresses the quantum statistics for identical particles, and in addition it calculates the canonical partition function, and the implications of the quantum statistics for particles when they get close are also addressed towards the end of the movie. I hope it's enjoyable and useful for students. This video is about the formulation of quantum statistical mechanics, and as usual, when we face a quantum problem we start by writing up the Hamiltonian. In fact, we don't specify the form of the Hamiltonian, but we just assume that it is an expression, an operator, which we can write as a function depending on the quantum numbers, the quantum operators corresponding to n indistinguishable particles. In order to analyze the effect of the indistinguishability, we introduce an operator Pij, which is a permutation operator. Well, in fact it's only an exchange operator. It exchanges particles I and j in the system, which means for the Hamiltonian that the quantum numbers of particle I and j are exchanged, and because the particles are indistinguishable, that should have no effect on the Hamiltonian. Formally, the Pij is defined by its action on a many-body wave function. So here we have a wave function psi, which depends on the quantum numbers of particles I and j. We call them xj. They may be the positions of these particles, but they may also include other variables like spin. And we see that the effect of Pij is to exchange the xj and the xi. Because the particles are considered to be indistinguishable, we should have that the commutator between the Pij, well, the Pij obviously is an operator, the h is also an operator. The commutator between these two should be 0, because Pij doesn't have any effect on the Hamiltonian. And we know from algebra that if two operators, let me put the hats on top of them, if two operators commute and they are both Hermitian, like is the case for the Pij and the h, then they should have simultaneous eigenstates, which means that there are eigenstates which are eigenstates of h, and simultaneously they are eigenstates of the Pij. The eigenvalues of h are usually denoted as E, that's the energy, and the eigenstates of Pij are just the eigenvalues of Pij's, we call them just lambda. And we have the following property for the Pij. If we apply it twice, we exchange I and j twice, so nothing changes in that case, and we are back at the unit operator. We haven't done anything if we exchange twice. Well, from this we can infer that, of course, acting with Pij squared on an eigenstate, then we get an eigenvalue lambda squared. And because the result of P is then itself the unit operator, the lambda squared should be 1. Furthermore, lambda should be real, because Pij is an emission operator, and therefore we can conclude that lambda is either +1 or -1. So we see that under exchange of two particles I and j, the eigenstates are either symmetric, that's when we have a +1, or anti-symmetric, and that's when we have a -1. And in this context, the spin statistics theorem is extremely important. It is a theorem which was derived in the 30s by Pauli and other people, and I will not prove it here, but the conclusion is that half-integer spin particles, they always have lambda is -1, so they are anti-symmetric, and we call them fermions. And particles with integer spin always have lambda as +1, and they are called bosons. For two particles the situation is rather simple. We have, for example, two particles with quantum numbers x1, x2. They are in a two-particle state psi, and we can write that as follows. This is just an example of a antisymmetric wave function. We have a 1 over square root of 2, and then we have particle 1 being in the state chi1. So please note the difference between the x1, that is the quantum numbers of particle 1, and this is the state the particle is in, so that's chi1. Particle 2 is in state chi2, and we have plus or minus particle 1 being in state 2 and particle 2 being in state 1. And because we have the plus and the minus sign here, it's easy to verify that the plus sign says that if I exchange particle 1 and 2, so I exchange 1 and 2, I have the same state. So that corresponds to lambda, the eigenvalue of that operation being plus 1. If there is a minus here, then the overall wave function changes sign, and that's the Fermion case, which I have up here. The next step is then to go to larger number of particles, arbitrary numbers of particles. Here we take n particles, and we can write the Fermion wave function as indicated by the f here, in the form of a so-called Slater determinant. So it's a kind of symbolic notation. The Slater determinant. So what we do is we take first a factor of 1 over n factorial square root, and that's just for normalization. And then we take particle 1 in state 1 up to particle 1 in state n. Here particle 2 in state 1, particle 2 in state n, and so on until we have particle n in state 1 up to particle n in state n. So we should be correct. And so we work this out just as a determinant, and because if a determinant is antisymmetric whenever we change two columns, and that guarantees that this wave function is antisymmetric under particle exchange. Another way of writing this wave function is the following. We have the same prefactor for the normalization, and this is a sum over p, and p denotes any permutation of the numbers 1 up to n. So we sum over all the possible permutations, and we have then here this mysterious epsilon p, that's the sign of the permutation, and the sign depends on how many exchanges I have to perform in order to realize the full permutation. Any permutation can be constructed from particle swaps, and the number of these swaps can be odd or even. If it's odd, we take a minus 1 for the epsilon p, and if it's even, then the epsilon p is plus 1. And then we have the one particle wave functions, where the particles themselves are labeled just in the order 1, 2, 3 up to n, but the states the particles are in are permuted, so we have p1 up to pn. It would also be possible to swap this, to have the permutations acting on the x and not on the x on the chi states. That would just be chi1 up to chi-n. And it doesn't matter because we sum over every permutation anyhow. And so the end result would be the same. So the sign is plus or minus 1. And an important consequence of this form of the wave function is that we can have at most one particle per orbital, which is known as Pauli's principle. And the reason is that if there would be two particles in an orbital, so if an orbital would be doubly occupied, you would find that two columns in this determinant would be identical, and a determinant with two identical columns vanishes. So in that case we get 0. So we should have at least, at most, one particle in an orbital. An orbital can be empty, or it can contain one particle. It cannot contain two particles. So we have found a general form for a Fermion wave function, and you may ask now yourself, is it also possible to write up something similar for bosons? And the answer turns out to be yes. So comparing this expression for the Fermion wave function with this expression, we see, of course, there should be a 1 over square root n factorial here. But if we sum here over all the permutations, and now we don't include the sign of the permutation, so each permutation occurs with the same sign, then it's obvious that this gives you a symmetric wave function. However, the normalization of this state is less trivial than in the case of the fermion wave function. In the fermion wave function, putting in 1 over square root of n factorial in front of it was enough to have a normalized state. That turns out not to be the case for bosons. For bosons, there may be more than one particle per orbital, and the normalization of this state is as follows. We get an n1 factorial, n2 factorial, etc., where the little n1 and n2, etc., they give you the occupation, they represent the occupation of orbital number 1, orbital number 2. Let us work out a simple example. As an example, we take two particles, 1 and 2, and they are both in the same state, which is chi. So the wave function then is x1 in chi and x2 in chi, and if these two orbitals are nicely normalized, then this is a symmetric normalized state. If we swap x1 and x2, we get the same state. But now let us try to follow the prescription here of the boson state for this case. Then we obtain the following. We have an x1 in chi. Obviously there should be a 1 over square root of 2 factorial in front, and we have x2 also in state chi, but we should have another term in which 1 and 2 are permuted because we sum over all the permutations. x2 chi, x1 chi, and we see that both terms are the same. So we have a square root of 2 factorial and then x1 chi, x2 chi. So we are square root of 2 factorial of, and that's precisely what this formula says too, because this is the norm squared, and so in that case we would just have the square root of 2 factorial squared, which gives me 2 factorial. Up to now we have made frequent use of these one particle orbitals, which are called chi, and they can play a special role in the case where we have a non-interacting system. So for example, if we have a Hamiltonian, a quantum mechanical operator obviously, which is the sum of one particle Hamiltonians, which means that these particles are free because they have no interactions. And if we have such a case, then it turns out that the anti-symmetrized and symmetrized wave functions we have considered above are eigenfunctions of this Hamiltonian, provided that the chi-j's are eigenstates of the one particle Hamiltonian. So I take one of these little h's, they act just on one particle, and if the chi-j's are eigenstates of that, then all the linear combinations that we have seen above, the anti-symmetrized and the symmetrized product states and linear combinations of them, they are eigenstates of the total Hamiltonian. Now generally we are interested also in interacting particles, and so you may ask yourself, what's then the use of these chi orbitals? Well, if the Hamiltonian contains interactions, then obviously these wave functions, they are no longer eigenstates of that Hamiltonian. And the problem of an Hamiltonian with interactions is tremendously complicated, but often people use basis sets which which have the form like this, just as a basis in the Hilbert space, because the Hilbert space of particles, whether they interact or not, in many particle Hilbert space is the same for non-interacting and interacting particles. And so these wave functions we have just studied, they are used very frequently to express the physics